Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this lecture, we are going to discuss A/B testing. If you don't know what A/B testing is, we can describe it with a realistic scenario. So suppose you run a software as a service startup, and you have a landing page where you give people information about your services and try to get them to sign up. We consider a user successfully signed up when they enter their email address and hit the sign up button. Of course, not every person who visits your landing page is going to sign up. Some people will read a bit, determine they are not interested, and leave your site. So you're going to have a conversion rate, the proportion of people who sign up that visit your landing page. Now suppose your lead marketer has determined that there are all sorts of things wrong with your landing page. Maybe the design isn't responsive, or the colors you chose didn't look good, or you didn't describe your company in a compelling way. So your lead marketer says you should try this new landing page they made, since they think it will lead to higher conversion rates. Because you're a data scientist, you would like to measure which landing page is better using data and math. Now this is where the concept of confidence intervals comes into play. Why did we talk about confidence intervals? Because we knew intuitively that 1 out of 10 is not as accurate as 10 out of 100, which is not as accurate as 100 out of 1000, even though these all yield the same click rate or conversion rate. Because of this, we also know that if one page gets 1 click out of 10, it's not necessarily worse than the other page which gets 2 clicks out of 10. What about if one page gets 10 clicks out of 100 and the other page gets 20 clicks out of 100? Now we are more certain. The question again is, how can we quantify this? The answer in frequentist statistics is to do a traditional statistical test. We'll go through a simple example in this lecture to set up the terminology and the general steps one takes in a statistical test, and in later lectures we'll look at more specific tests that we can use. To start, we'll use a more simple scenario. So suppose we're measuring the heights of men and women, and we would like to know, are men taller than women? In a statistical test, you would say, is the difference in height between men and women statistically significant? So there's that term significance again, which we first saw with confidence intervals. Recall that we use the symbol alpha to represent it. We will again use 5%, which is a standard significance level that researchers use. Researchers also use 1%, which requires a more significant difference between the two samples. But this highlights a weakness of this method. We still need to choose what threshold we deem to be significant. To be even more precise, what we are measuring is the difference in mean height between men and women statistically significant at significance level alpha? So in statistical testing, we have two hypotheses. The first we call the null hypothesis. Usually this represents there being no difference. So for example, the null hypothesis is that there's no significant difference between the mean height of men and the mean height of women. As another example, it could be that there's no significant difference between the effect of a new drug and a placebo. The alternative hypothesis can be one of a few things. It can be that the mean height of men is greater than the mean height of women. We call this a one-sided test. It can also be that the mean height of men is not equal to the mean height of women. We call this a two-sided test because it means that the mean height of men can be different in the sense that it could be greater than or less than the mean height of women. Similarly, it could mean that using the drug leads to worse results than a placebo, or it could mean that using the drug leads to better results than a placebo. We will be doing the two-sided test, or in other words, our alternative hypothesis will be that the average height of men is not equal to the average height of women. In the next lecture, we'll look at how to quantitatively show that the two groups are statistically significantly different. Hey everyone, and welcome back to this class, Bayesian Machine Learning in Python. In this lecture, I'm going to introduce you to another exercise on the chi-square test. We are going to use the same data file as we did for the t-test exercise. That's advertisementclicks.csv. Remember that we have two columns here. The first column represents which advertisement, and the second column represents click or no click, represented by 1 and 0, where 1 is click and 0 equals no click. Both count as impressions. Since we've already seen some code that can perform the chi-square test, I'll assume you don't need too much direction for this exercise. One important concept to discuss with this exercise follows from one of the key concepts from the previous exercise. Recall that this important concept was that all data is the same. So the same data can represent an A/B test for two different logos or an A/B test for two different news article headlines. In the same vein, we can now see that all algorithm interfaces are the same. What do I mean by that? That means I can plug in this same data into a t-test that I can plug into the chi-square test. The data did not change. In a broader machine learning context, this is why you can use different classifiers on the same data. For example, suppose I train a neural network to predict whether or not a user will buy something on my website. Well, now suppose I want to ask, will a random forest perform better on this dataset? And of course, all I need to do is just plug in some data into the random forest and check the result. The data itself doesn't need to be transformed in any way. The interface for the data is the same in both cases. So we say all algorithm interfaces are the same. So go ahead and try the chi-square test on our dataset. Again, this is so simple that I'm not going to walk you through my solution, but you are strongly encouraged to share your solution on the discussion board. The relevant file in the course repo is ex_chi-square.py. Your job again is to determine whether or not the difference in click-through rates is statistically significant. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python Part 1. In this lecture, we are going to discuss how to do A/B testing when you want to test more than two groups. This is a very practical thing to want to do. For instance, you could have 3 or more advertisements you want to test out, or 3 or more different landing pages. So one thing about p-values is that it's possible to get a significant p-value by chance, just by doing more experiments, as we saw. One controversy about p-values is that you can just run a bunch of experiments and work backwards to pick something that you found had a statistically significant p-value. One easy solution to testing multiple groups is the Bonferroni correction. All we do is divide the significance level alpha by the number of tests we perform. One method of comparing multiple groups is to do pairwise testing. So test every group against every other group. There are n choose 2 pairwise tests to perform, and so the Bonferroni corrected significance level, we use alpha divided by n choose 2. That means any p-value we find has to be less than this to be statistically significant. Another method is to do one versus the rest testing. So if we have n different groups, then we'll do n different tests. To calculate the data for the group that counts as the rest, we sum the counts for all those groups. Note that we also apply the Bonferroni correction here, so the new significance level would be alpha divided by n. Lastly, I'll mention that what I just described is typically called post hoc testing. It means that the first test we do is on the full contingency table, which will be bigger than 2 by 2. It'll be n by 2 for n groups and 2 possible events. If we get a significant p-value for that, then we would follow up by doing post hoc testing. As with most of the other frequentist A/B testing concepts we've looked at, you'll see that later when we do Bayesian A/B testing, the fact that we have multiple groups will be handled elegantly without any extra work. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python Part 1. In this lecture, we are going to take a closer look at statistical power and relate it to concepts we already know about. You may have noticed that we haven't yet quantitatively defined power. In fact, we can relate it back to our discussion about imbalanced classes. In this context, power is actually equal to sensitivity. We say that power is equal to the probability that we reject the null hypothesis given that the alternative hypothesis is true. So how do we get to this? Well, first recognize that this is like a binary classification problem. We have two possible truths, that either the null hypothesis is true or the alternative hypothesis is true. And then we have two predictions, reject the null hypothesis or do not reject the null hypothesis. Note that these predictions are not accept the null hypothesis and accept the alternative hypothesis. This sort of tippy-toeing around the correct definitions is yet another reason why traditional A/B testing is undesirable. It's both confusing for the data scientist doing the work, and it's hard to communicate to non-technical people, and it's very likely things will get lost in translation. So just for completion, we're going to go over some more statistics definitions. However, it's not necessary to remember the names of these, because like most things in statistics, they are just complicated words that represent more fundamental concepts in probability that we already know about. So a high power decreases the chances of getting a false negative, and a false negative is also known as a type 2 error. The probability of getting a false negative, or the false negative rate, is called beta, and it is equal to 1 minus power. Therefore, power is also equal to 1 minus beta. On the other hand, we also have type 1 error, which is also called a false positive. As you can see, it's highly desirable just to stick to the fundamental concepts, which are true positive, true negative, and false negative. So why do we want to quantify statistical power? Well, one of the main reasons is that power analysis can be used to determine the number of samples we should obtain in our experiment. We've already discussed some of the things that affect the power of a test, but two key ones are the effect size and the sample size. The effect size, or in other words, the difference between the two groups, matters because we know a big difference is easier to measure than a small difference for a given variance. The sample size matters since, as you've seen, it also directly influences the test statistic, and thus the p-value. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this lecture, we are going to talk about a major pitfall when it comes to A/B testing. In our code, we observed the behavior of the p-value as the experiment progressed, but that was just to get a sense of the way that it can change. In reality, you shouldn't check the p-value until your experiment is over, because, as you know, it can show significance and then go back above the significance threshold. Sometimes, people will stop their test early once they reach significance, and this lecture will explain why you shouldn't do that. There are even some software packages out there that let you do this with a built-in feature. Luckily, we are Python coders, and we don't use crusty old statistical packages. Let's review the definition of p-value. It says that if group A and B are the same, we will observe a difference this size or greater 5% of the time. So this means 5% of the time, we expect to get this very small p-value, even though A and B are exactly the same. Now, if we look at the ways the p-value can progress, we can see that there are a few different scenarios to consider. The first is that the p-value can remain at insignificant levels. The p-value can become significant after a number of trials. The p-value can be significant at first and then settle into insignificance. And lastly, the p-value can remain at significant levels. Let's now look at the effect of stopping once we see significance. So you see that in one case, where it's possible that the p-value can go from significant to insignificant, we would never catch that. The end result is that we've increased the proportion of time we detect significance when A is equal to B. So it's a bad thing to stop early, and as a general rule of thumb, it's advised to choose your sample size before the experiment starts and to stick to it. So how do we choose sample size? One general rule of thumb is n is equal to 16 times sigma squared divided by delta squared. Here, sigma squared is the variance of the data, and delta is the minimum difference you want to detect. Recall that smaller differences are harder to detect, so it'll require a larger n. There are also a ton of sample size calculators online you can use, but they all require you to make assumptions or estimations about your data. The strange thing about frequentist statistics is that all these rules are kind of counterintuitive and awkward. In some cases, you might even consider them unethical. As an example, imagine you are testing a drug, and due to the fact that you know the science behind it, you are very confident that it will work. Then you start your test, and it's clearly performing well. But the rules of statistics say you can't stop your test early and give the drug to everybody. You need to wait until the test is over. Another example is conversion rate. Imagine that you are absolutely certain, after a small number of page views, that one landing page is converting better than the other. You'll be very tempted to just switch to the better landing page so you can start making more money. But statistics says to not do that. We'll see later how Bayesian methods solve this problem. Typically, Bayesian methods require less samples in order to pass some threshold. You can also stop an experiment at any time and calculate exact probabilities directly from the data you've collected. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python Part 1. In this lecture, we are going to summarize everything we've learned in this section. Traditional statistics is pretty confusing, so it's okay if you don't get it all the first time. The important thing to ask yourself is, how can I use this on real data? The act of answering this question will really help you understand it all better. The first thing we looked at in this section was the t-test. Sometimes people call this the student t-test because the guy who invented it published it under the pseudonym student. The t-test is for comparing two different groups of Gaussian distributed data. It's typical that people use this test for data that isn't exactly Gaussian distributed, but as we discussed, there are other tests that don't make such assumptions about the data, called non-parametric tests, that might be more suitable. At the same time, because those tests make less assumptions about the data, they have less power. We use the t-test to introduce you to the concept of statistical testing, but the steps are the same no matter what test you use. In particular, we first define a null hypothesis and an alternative hypothesis. The result of the test is either that we'll reject the null hypothesis or not reject the null hypothesis. Remember the important distinction here. Failing to reject the null hypothesis is not the same as accepting the null hypothesis. If there is indeed a difference between the two groups, it could be that you didn't collect enough data for the difference to be detected. Also remember that if the variance of the two groups is large, you'll need a lot more data to detect the difference. More data means your test has more power. The next step is to calculate your test statistic, which is a function of random variables, so it is also a random variable and has a probability distribution. With the t-test, the test statistic is t-distributed. With the chi-square test, the test statistic is chi-square distributed. In both these tests, extreme values represent the fact that the two groups are different. With the chi-square test, because the chi-square distribution is only positive, there is only one tail, which is on the right. With the t-test, which is a symmetric distribution that looks like a Gaussian but with fatter tails, there are two tails, so you can do a one-sided test or a two-sided test. The last step is to calculate the p-value. Remember that the more extreme your test statistic is, the smaller your p-value will be. Researchers typically use p-value significance thresholds of 5% or 1%. There are many drawbacks to traditional statistical testing. The first is that it's very confusing. And you're already a data scientist, and this is your field. Imagine how confusing it's going to be to communicate this information to someone who is not a data scientist. Another drawback is that repeated testing increases your chances of finding a significant effect when there is none. Remember that p-value is the probability of detecting a difference, even when the two groups are the same. So if you're doing repeated testing or you're testing multiple groups, you shouldn't go fishing for significant effects, and you should use the Bonferroni correction. Lastly, you should never stop your test early when you see a significant p-value, because that increases your chances of getting a false positive. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this lecture, we are going to continue with our example of comparing the height of men and the height of women, or drug effect and placebo effect, and show you how to come up with a solution quantitatively. As is typical in frequentist statistics, we are going to assume that our data is normally distributed. So both the height of men and height of women come from a Gaussian distribution, with possibly different means. So what we do is we collect some data, so we measure some people, and now we have two lists of heights, one for men and one for women. Next, we create what is called a test statistic. Let's call it T, and it is equal to the mean of x1 minus the mean of x2 divided by S of p times the square root of 2 over n. So S of p is called the pooled standard deviation, and as you can see, it's the average of the two individual standard deviations. Note that these standard deviations are the unbiased estimates, so we divide by n minus 1 rather than n. Note that n is the number of samples collected for one group. So if you have 10 men and 10 women, then n is 10. If you have groups of unequal lengths, you need to use a different formula for the pooled standard deviation and the test statistic, but we'll leave that out for simplicity. So if you think back to when we were looking at our estimate of the mean, we said that because it was a sum of random variables, it was also a random variable, and we showed that its distribution is Gaussian. If you look at this test statistic that we just calculated, you'll notice that it is also a function of random variables, so it is also a random variable. The next step is kind of hand-wavy because it can be shown that the test statistic we just calculated is not Gaussian distributed, but rather t-distributed. You'll see the t-distribution, along with some more exotic distributions, quite a bit when you're studying statistical testing and Bayesian methods. So what is the t-distribution? Basically, it looks a lot like the Gaussian distribution, but it has fatter tails. That means there is more probability weight on the tail ends compared to the Gaussian. If you recall, the Gaussian drops off exponentially by x squared, which is a very fast drop-off. The t-distribution has a really complicated formula for the PDF, but we won't be using it in this course. Notice that there is only one parameter here, the Greek letter nu, which we call the degrees of freedom. Nu controls how wide or skinny the PDF is. For our statistical test, nu is equal to 2n minus 2. Similar to the Gaussian, the t-distribution can have a mean and scale parameter, but again, we won't be using those in this course. So let's look at the formula for the test statistic again, and examine how the value of t might change under certain conditions. You can see that if the mean of x1 and x2 are the same, then t will be 0, so it falls right in the middle of the t PDF. This would be the situation where the height of men and women is the same. What if the mean of x1 and x2 are very different? Well, then t will be either very large or very small. Notice that, like the Gaussian distribution, the t-distribution is also symmetric. So it doesn't matter if x1 is men and x2 is women, or if x1 is women and x2 is men. We'll still get either a positive test statistic or the negative of that same test statistic. We'll examine this formula more in depth later, but for now let's move on to the next step. So similar to the problem of finding a confidence interval, we want to find the area under the curve of the t-distribution, so we'll need the CDF. Also remember that there are two tails of the distribution we need to consider, the left and the right. If we are at the extreme left, then the area will be very small, so we'll get a probability close to 0. If we are at the extreme right, then the area will be very close to 1. So for a significance level of 5%, then we want to be either at the bottom 2.5% of the area on the left or the top 2.5% of the area on the right. If that is the case, then we can say that the difference between our two groups is statistically significant. Unfortunately, this isn't the whole story in terms of learning about statistics terminology. Algorithmically, we are done. We know how to show that the two groups have a significant difference. There's just more terminology and definitions that are used in statistics that we want to know about so we can apply them in later lectures. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In the previous lecture, I showed you an algorithm to determine whether the difference between two groups was statistically significant. I said that we were done, but there is a little more terminology in statistics to talk about, since we'll be using it later. In statistics, if the two groups are different, then we are looking for one number, which should be a very small number in both cases, no matter which tail end you are on. Now, why are we looking for this very small number? Well, it's called a p-value, and there is lots of controversy over its use and its precise meaning that even today you can find people discussing it online. It's not our goal in this course to discuss p-values in depth, because we are more interested in getting to the Bayesian way of doing things. So the internet official definition of p-value, courtesy of Wikipedia, is the probability of obtaining a result equal to or more extreme than what was actually observed when the null hypothesis is true. So just to rephrase that in terms of our example, what we're saying is, if the average height of men is equal to the average height of women, and remember that is our null hypothesis, then the p-value we get is the probability of observing the difference we measure, or any larger difference. In other words, if the magnitude of our test statistic, and remember it's proportional to the mean of x1 minus the mean of x2, if this is very large, then the p-value we get should be very small. Also, we want to keep using our significance level alpha. So if the p-value is less than alpha, we say the difference is statistically significant and we reject the null hypothesis. Otherwise, we cannot reject the null hypothesis. Note that this does not imply that the null hypothesis is true. It just means we can't reject it with the data we collected. So for our two-sided example, we want the p-value to be less than 5%, or 0.05, which is a typical significance level. Suppose our result is statistically significant. With the t-distribution CDF, that means we'll get a number either less than 0.025 or greater than 0.975. If we get a number greater than 0.975, we take 1 minus that number, and then we'll get a number less than 0.025. Okay, so now we have a way to get a very small number in either case, whether x1 is bigger than x2 or x2 is bigger than x1. Now notice the threshold of this small number is 0.025 rather than 0.05, which is our significance level. So what we do now is we just multiply our small number by 2. This way, the threshold for this new number is 0.05, which works with our predetermined significance level. And this is what we call our p-value. Last thing I want to mention is that this multiplication by 2 is only used for the two-sided test. For the one-sided test, where we are only checking if x1 is greater than x2, we would not multiply by 2 since we are only interested in one tail. In this way, we say that the one-sided test has more power than the two-sided test because it doesn't require a test statistic as extreme to be significant. In general, the more assumptions you make, the more power your test has, and the opposite is also true. The less assumptions you make, the less power your test has. We'll see this concept again later. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. As promised, we are going to go back to our equation for the test statistic, and we are going to examine it a little more closely. We already know that if the mean of x1 is much bigger than the mean of x2, or vice versa, then that will make the test statistic larger in magnitude. But there are two other variables here that t depends on, the pooled standard deviation and n. So notice that n is in the denominator of the denominator, so effectively t is proportional to the square root of n. This is interesting because it tells us that a larger n leads to a bigger t. Why is this important? Well, it tells us that if x1 and x2 are different, then the more samples we collect, the larger t will be, and thus the smaller the p-value will be. So for the same x1 and x2, large n might lead to a significant difference, while small n might not. Next, let's look at the standard deviation. Basically, this is saying that if the variance of the two groups is large, it'll be harder to find a statistically significant difference. There will be too much overlap between these two groups. Compare that to the situation where we have the exact same mean, but much skinnier variances. The distributions hardly overlap, so it's easier to show a statistically significant difference. Next, let's look at how the test statistic changes with the pooled standard deviation compared to n. In fact, this should remind you a lot of the confidence interval. If you recall, the standard deviation of the confidence interval was proportional to the standard deviation of the data, but only inversely proportional to the square root of the sample size. Therefore, we need a lot more data to account for a little bit of standard deviation. We have the same situation for the test statistic. The test statistic only grows or becomes more extreme with the square root of n. At the same time, t is inversely proportional to the standard deviation. So if you're trying to find a significant difference, then you'll need to collect a lot more samples to account for small deviations in your data. If you read online forums, sometimes you'll see people comment on a scientific study that finds a statistically significant effect, and they'll say something along the lines of, "This study only has 20 participants, so therefore it's a garbage result." So now that you know how the t statistic is calculated, you can see that the logic in this statement doesn't follow. Why is that? Well, the t statistic actually depends on n, so if n is small, the t statistic is lower. So finding statistical significance is actually a function of n, so it already takes the sample size into account. Therefore, it's not correct to just say that the value of n makes a finding false. Alright, so let's look at the pooled standard deviation next. Actually, for this we have to return to n. Recall that n is both the number of men and the number of women. But what if we have two groups of different sizes? Then the pooled standard deviation will be a weighted combination of the two. We won't do this since it's a pretty trivial change, but here are the formulas. Continuing on with our assumptions about the pooled standard deviation. This one is perhaps not as obvious, but one big assumption we've made is that the variance of the two groups is the same. That seems like a pretty strong assumption, so there is a modification called Welch's t-test, which does not make this assumption. The important thing, though, is that the steps are the same. Find the t-statistic, find the degrees of freedom, and calculate the p-value to see if it's significant. The final assumption we'll talk about is the Gaussian assumption. A lot of data, including our click data, is not Gaussian. We will see what type of test to use on click data in a later lecture, but what if you don't know what distribution your data comes from at all? Well, there are tests called non-parametric statistical tests that don't make these assumptions. These are also called distribution-free tests. Some popular ones are Kolmogorov-Smirnov test, Kruskal-Wallis test, and the Mann-Whitney U test. So these are all in SciPy, and you can check the SciPy API to see how they work. We won't be using these, but in general the API for these is all the same. So it's similar to how no matter what machine learning model in scikit-learn you use, they all have the fit and predict functions. So once you learn how to plug your data into one test, it'll be similar for the other ones too. One thing to note about these non-parametric tests is that because they make less assumptions, they have less statistical power than if you had done something like the t-test. What this means is that there would need to be a more extreme difference in your two groups to get a statistically significant p-value. We saw this earlier as well. Since the one-sided t-test makes more assumptions than the two-sided t-test, the one-sided t-test has more statistical power. One of the assumptions we looked at but did not make was the fact that we could do a one-sided test. We instead chose to do a two-sided test. For comparing heights, we could have used a one-sided test because we already know that men are taller than women on average. The effect on the p-value is that it's easier to achieve a significant difference, because we're no longer multiplying our area under the curve by 2. But there are some cases where you absolutely do not want to assume you're doing a one-sided test. Think about if you're doing drug testing. You might intuitively think that you want to measure the improvement this drug makes in the patient's condition, but ethically we need to test for the opposite scenario as well. If the drug worsens the patient's condition, that's a bad thing. However, if you have a drug that already works effectively, and you want to test if another drug works more effectively, then you can use a one-sided test for that. So to summarize, the point of this process was just to show you a simple example of how frequentist statistical testing works. We generate a test statistic, and from that we know its distribution. We look to see if the test statistic is at the extreme values of the distribution to see if what we measured is statistically significant. And if it is statistically significant, we reject the null hypothesis. Hey guys, welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this lecture, we are going to write the t-test in code. If you don't want to code along, you just want to run the code, the relevant file is ttest.py. So we're going to start by importing numpy. And let's import stats from SciPy. First step is we're going to generate some data. So 10 data points for each group. A is equal to Gaussian distributed data of size n, and the mean will be 2. B is going to be the same thing, but the mean will be 0. These both have variance 1. So for this first part, we're going to roll our own t-test. So we're going to calculate the variance of A, so that's a.var, and now by default, NumPy does the maximum likelihood estimate of the variance. So that's dividing by n. We want the unbiased estimate, which divides by n minus 1. So we pass in ddof equals 1. And for var b, we do the same thing. The next step is to calculate the pooled standard deviation. So that's the square root of variance of A plus variance of B divided by 2. Next step is to calculate the t-statistic. So this is a.mean minus b.mean. We divide by s times the square root of 2 over n. Next step is to calculate the degrees of freedom. We have to pass that into the t-distribution CDF. So that's just 2 times n minus 2. Let's get the p-value. So that's 1 minus stats.t.cdf. We pass in the t-statistic, and the degrees of freedom is equal to df. And let's print out the result. So we'll print out the t-statistic, and we'll print out p. We are almost done. We have to multiply p by 2, and that is the p-value. And just to compare with the built-in SciPy function that does this, we'll get t2 and p2 from stats.ttest ind. So ind stands for independent. Pass in a and b, and print the same information, t2 and p2. We don't need to multiply this by 2 because it's already done by SciPy. Okay, so let's run this and see what we get. Cool, so we get the same answer for both cases.
Hey everyone, and welcome back to this class, Bayesian Machine Learning in Python. In this lecture, we are going to do an exercise on applying the t-test to some data. Contrary to what we discussed in the previous lectures, we can still force the t-test to work on our click-through rate data. The first thing we're going to do is look at the file we'll be working with. In the course repo, this is advertisementclicks.csv. As you can see, at the top we have some header columns. The first column tells us which advertisement we're looking at, and the second column tells us whether the action was a click or a no-click. So for each row, we know that the user has seen an advertisement, and then 1 means they clicked on it, and 0 means they did not click on it. The first thing you'll need to do is check how many different advertisements you're comparing in this file. That will determine whether or not you need to use the Bonferroni correction. Once you've done that, you'll want to perform the t-test as we demonstrated earlier. Your job is to answer the question, does one advertisement have a better click-through rate than another, as determined by statistical significance? Since you also know about the multiple types of t-tests that can exist, for example, there's a t-test for where 2 groups have the same variance, and there's a t-test for where 2 groups have a different variance, you'll want to pick the right one. Or you can try each of the different types of tests and compare the answer you get. One key point about this exercise that I think a lot of people don't realize is that it doesn't really matter where this data came from. I told you earlier that this data represents click-throughs on various advertisements, but that need not be the case. In fact, this data could be about news article headlines. What would I do if I wanted this data to represent news article headlines? Well, I just replaced the header of the data file. This is what we mean when we say all data is the same. So a lot of people ask me, well, what if we want to compare 2 different landing pages, or 2 different website designs, or 2 different logos, and so on? Well, the key point is the structure of the data doesn't change. Therefore, the program that you write to process the data doesn't change. Remember that all the computer sees are the numbers. So when you do this exercise, remember that what you're really doing is you're doing all of these comparisons at the same time without even knowing it. Eventually, I won't need to tell you that this data can represent different landing pages or different logos. You already inherently understand that. So if you're wondering how this crazy math applies to your data, well, this is how. Now, a second question related to the previous question that I often get is, well, how do I collect this data? And of course, that's a question only you can answer. If you're working at a company and your data is stored on Hadoop, then maybe you'd write a script to get your data off Hadoop. Maybe you'd write a MapReduce or a Spark job. Maybe your data is from your own website, and your website is written in PHP and MySQL. Then you need to write a script that can grab the data from your MySQL database. Maybe your data is collected by third-party software as a service, and you can download it as a CSV from their website. Of course, the possibilities are endless, but the point of this slide is to make sure you understand the separation of responsibility. So there's the machine learning side, and then there's the data engineering side. The part where you get the data would not be considered machine learning. That would just be regular programming, or even maybe it's not even programming, it's just navigating to a website and figuring out how to download the right CSV. However, this course is about machine learning, so we assume you have the data at your disposal and that you have the programming skills to get the data into the expected format. And of course, this necessitates that you understand what the right format is in the first place. So make sure you understand the difference between the machine learning parts and the non-machine learning parts, as this will help you not only digest the contents of this course more easily, but it will help you understand this very important concept that all data is the same. Since this exercise is quite short, I'm not going to walk you through the answer, but you are encouraged to write a solution and share it with your fellow students on the discussion board. If you want to look at the code that I wrote, check out exttest.py in the course repo, but I'd encourage not looking at that until you've given this exercise a fair shot. Good luck.
Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this lecture, we're going to discuss the kinds of numbers you'll see when you do A/B testing. A lot of the time, click-through rates are very small, and conversion rates are even smaller. We're talking on the order of 1 or 2%. The significant differences you find could be even smaller than that, maybe 0.1%. This seems insignificant overall, so why should you even care? Is it worth putting in engineering effort to build a new landing page just to improve your conversion rate by 0.1%? The answer is maybe, but you need to do an actual analysis to determine your break-even point and whether or not it's actually worth it. Consider if you have 1 million visitors per day and 1% of those people buy your product. Let's say that every product you sell nets you $20. Then from that 1% of people, you're making $200,000. Well, if you could increase that conversion rate to 1.1%, then you'd be making $220,000. That's a $20,000 difference. Not bad for just changing the landing page. So the lesson in this lecture is, don't be dissuaded by significant differences that seem insignificant because they are small. Remember, the test statistic takes n, which is the number of samples, the variance, and the difference between the groups into account, all at the same time. You want to do further analysis to show in terms of value whether or not making a change is worth it. Hey guys, and welcome back to this class, Bayesian Machine Learning in Python Part 1. In this lecture, we are going to look at a more complex statistical test, one that works for click-through rates and conversion rates. Now that you know the basic steps of a test, it should be easier to extend to more tests. This statistical test works on what we call a contingency table. So this is for categorical variables where we are adding up counts. Along the rows we have each group. We'll call this advertisement A and advertisement B. Along the columns we have the events, click or no click. We would like to know if the difference in click-through rates between advertisement A and advertisement B is statistically significant. Once we have this table, we calculate what is called the chi-squared test statistic. It is called this because, of course, it is chi-squared distributed. Recall that I mentioned you're going to see a lot more exotic distributions than just the Gaussian and the Bernoulli when you dive into the world of statistics. Values in the chi-squared distribution are always positive, and like the t-distribution, its main parameter is the degrees of freedom. Also like the t-distribution, the location and scale parameters are not mentioned in their Wikipedia pages, but in SciPy you can pass them in. We will be using the default location of 0 and scale of 1. So let's look at how the chi-squared test statistic is calculated. It is equal to the sum over all I, so I is equal to every cell in the table, the observed cell minus what we expect to see there. You square that and then divide by the expected value. It's pretty clear that this is always going to be positive since the numerator is squared and the denominator is an expected value, which since we are counting things is always going to be positive. I personally didn't find this form of the equation to be very self-explanatory, so we are going to do an example. So first, the I indexes a cell in the table. So for example, it's going to refer to row 1, column 1, which is the number of clicks for advertisement A. We know the observed value because that's just the value in the table. But what is the expected value? Well, if we pool all the data together, we can get an estimate of the probability of a click, which is the total number of clicks over the total number of impressions. Then, if advertisement A is an average advertisement, then we would expect the number of clicks to be the total number of times we showed advertisement A times p click. Similarly, if we want to estimate the expected number of no clicks for advertisement A, we would first calculate the global probability of no click, which is column 2 divided by total number of impressions. We then multiply that by the sum of row 1, which is the total number of times advertisement A was shown. So we can go through that same process for each of the 4 cells in the contingency table, and this is the result that you should get. Take a minute to examine this and make sure it's the same as the answer you calculated. Okay, so that was a pretty complicated calculation, but luckily there's a shortcut. A chi-squared test statistic can be calculated from this simple formula, which of course only works for a 2x2 contingency table. I would highly recommend you prove on paper that this is equivalent to the previous equation. It's a purely mechanical exercise, so there isn't any complicated math you need to know. I would say it'll probably take you around 30 minutes to 1 hour to complete. So please do this, it's a good exercise. Next, what do we do once we have the chi-square test statistic? Since the test statistic is always positive and will get larger as the data strays from the average, then a large chi-square test statistic would be significant. Intuitively, we know that we are then looking at the far right of the chi-square distribution, and so 1 minus the CDF will give us a small number, which is the p-value. As usual, if this p-value is less than alpha, our significance threshold, we will say that the difference in click-through rates between advertisement A and advertisement B is statistically significant. Note that this test is also built into SciPy, so the process we discussed above would be equivalent to just calling scipy.stats.chi-square contingency, pass in the table, and correction equals false. So what exactly is this correction? An important fact is that the chi-square test statistic is only an approximation. You'll see this a lot in frequentist statistics, where we say, the chi-square test statistic asymptotically approaches the chi-square distribution. And by asymptotically, we mean as n approaches infinity. This is the same situation we have in the central limit theorem, and it's the same situation we have when we are estimating the mean of a random variable. It's only exact when n is equal to infinity. So what this also means is that there are other tests you can do for this same data set to get the same type of answer, and there are corrections you can make to the plain chi-square test as well. For example, in SciPy, you'll see that by default the chi-square test makes the Yates correction, and there is also Fisher's exact test, which both work on the same type of data. Again, all of these are plug and play, so the API for all of them is similar or the same.